which I don't know why I don't have to have some written consent from you, but, and I don't know. Anyways, so what did we talk about last time? We talked about, what did we talk about last time? Curl and divergence. And we talked about Green's theorem using curl and divergence. Just the curl, really, not the divergence yet. So the whole theme here is we want to move up in dimension. So just think about how we started this. The fundamental theorem of calculus talks about, fundamental theorem of calculus. This talks about functions like this over my intervals. So my regions are one-dimensional, right? And then Green's theorem talks about things like this, and my regions are two-dimensional. So now we want to go to larger and higher dimensional objects, right? And not just higher dimensional objects, but differently shaped higher dimensional objects. So what do I mean by that? The first thing we started on is the fundamental theorem of calculus, which has these nice flat intervals and functions on top of them. Then we went to these line integrals and then functions on top of these, right? So we went from flat one-dimensional stuff to curvy one-dimensional stuff. Green's theorem used flat two-dimensional stuff with curvy one-dimensional stuff. And we're going to move to curvy two-dimensional stuff with curvy one-dimensional stuff. Okay? And what does curvy two-dimensional stuff mean? Right? So Green's theorem is flat in the plane, but what if I want to look at, let's pretend this is three-dimensional here. A surface like this. This is now a curvy two-dimensional object, right? Okay, yeah, the numbers are, they're a bit glaring. Let me see if I can cover up the, spin those.
Helps. That helps. Thank you.
That's better?
Yes.
Okay, perfect. So this is what we're moving towards, right? I want to have a little roadmap of where we're going before we get really lost in all that shit we're going to be doing today. Okay? Flat one-dimensional with zero-dimensional boundary, right? These are just points. Curvy one-dimensional with zero-dimensional boundary. Flat one-dimensional, flat two-dimensional with one-dimensional boundary. Curvy two-dimensional with one-dimensional boundary. Okay? This is where we're going to go. Random pokey thingy, nail clipper. Okay? Any questions on what the plan is? Well, the really general plan. This is an actual plan, but these are the things we want to study.
It seems a little, I'm just a little confused. Like, is that for fundamental theorem, like, or talking about Green's theorem?
So Green's theorem is going to do this case. We did a new theorem here for this.
Okay, so the fundamental theorem was the first one, and then
yes.
Green's theorem. Okay.
Green's theorem does for that, and this was the fundamental theorem for line integrals. Right. So we had theorems for each of these, and we'll have theorems for things like this: Stokes' theorem and the divergence theorem. Okay. So to start talking about these things, we need to parameterize these surfaces. We need to describe them in an effective way, right? And why do we need to parameterize them? If we look back at line integrals, when we move to curvy, what's the thing we did? We needed to make a parameterization so we can describe movement on this curve, right? So if we want to describe movement on this surface, I have to have a parameterization. Slide on. Maybe this light makes it a bit better. No?
You
I
mean
don't
like
know. Huh?
you mean like a parameterized surface area?
We need to parameterize the surface. And then we can compute things like surface area.
Oh, okay, okay.
Right? So what does that mean by that? We parameterized the curves before, right? So recall, we had R of t equals to f of ti plus g of tj plus h of tk. This gave me a curve. Does this light make it better or worse? Light is on here, light
I'd
is
say
off
better.
here. Better?
I'd say better, but I solved some of my own problem here too by turning off the lamp.
Okay. Light is on then. This is a curve in R3. It has one independent variable t. We want to do things like this now. I call them S for surface. Nah, I'll stick with R. R, it has two variables now, u and v, and the functions are of two variables. This is a surface. R3. Right? So given a u and a v, I get a vector, and this points to a point in R3. As I change u and v, I draw a surface, just like I did curves before. The only difference now is we have an extra variable, right? So this makes this a two-dimensional object as opposed to a one-dimensional object. And it's a two-dimensional curvy object. Okay? Any questions about the object we're looking at here? No? So I'm going to say we're very familiar with this already, but let's look at a function. We have a function that says f of x, y equals z. Right? And we can say, for example, z is the square root of x squared plus y squared. What kind of shape is this?
Circle?
It's the,
Well,
I want 3 minus this. We'll do that.
oh, is it an ellipse? Or?
Is it an ellipse?
Sure, it's also a sphere. Ellipses are spheres. Oh, this is a minus sign. Now what's a sphere? It's the top half of a sphere of radius square root of 3, right? Because x squared plus y squared plus z squared equals 3 is a sphere with radius 3, square root of 3. So this is a sphere, the top half of a sphere of radius 3, square root of 3. Should have picked a better number than 3. If I want to make a parameterization like that, I want to write it in this form. What's an easy way to do it? I can parameterize this in terms of x and y, and then z is a function of both x and y, right? So I can say something like f of xy is equal to x. I'll make this u, sorry, and v. G of uv is equal to y, and h of uv is 3 minus x squared minus y squared. So then I can parameterize this surface just like this. R of t is R of xy is xi plus yj plus square root of 3 minus x squared minus y squared k. Okay? So this gives us the top half of the sphere. And I want to see that they're the same here. So we can draw the surface. This is the top half of the sphere. Z equals 3 minus x squared minus y squared to the 1/2. Top half of the sphere of radius square root of 3 looks pretty good. And I can draw a parametric surface right here, parametric surface, using this exact same parameterization. U B 3 minus u squared minus v squared to the 1/2. And I didn't draw the whole thing. U goes from okay. So the parameterization, I think, yeah. So do we agree we got the same thing?
Yes.
Do you see how we could parameterize any function? Right, so if I have a function, given any function, z equals f of x, y, we can always make this parameterization. Man, my writing is not doing super well today. So if I have a function, a parameterization for that surface is very easy. I pick my 2 independent variables as my parameters, and then my k value is just the function. That's that, right? Any questions about that? This should be exactly what we did in whenever we talked about parameterizing curves, but now in 2 dimensions. Okay?
I feel like you parameterize with u and v with the original function, and then you turn that into a like r of x, y.
Yeah, I mean, it doesn't really matter what parameters you choose,
Yeah.
right? Because, well, let me put some adjectives to that. It matters when the parameters you choose have units, or you're doing some application problem where the variables you choose have actual meaning, right? But x, y, u, v, t, c, whatever, in this general sense, doesn't mean anything, right? I have no restrictions on x, y, and u. All I need to do is, if I had put restrictions on x and u's and v's and y's and things like that, yes, then my choice of variable would matter. But there is really no difference. They're all essentially the same thing, right? X and u mean the same. They're just any possible real number, right? So if I had, but I do want to make a disclaimer, if I was doing this with some a problem that required some variables that had meaning, I would not be able to make this swift variable change, right?
That's what would confuse me, but I think I understand that.
Okay. So we got any graph. That's pretty easy. Now, how do we parameterize? So things we're going to need to know. Graphs, surfaces of a graph. That one's pretty easy. And planes. How do I parameterize a plane? So what does that mean? Given a point, x0, y0, z0 equals r0. and two vectors that both start at R0 and are not parallel. We'll call these A and B. Parameterize the plane spanned by them. Okay. So how do we draw this? I've got a point here. This is R0 right here. I've got A, it goes this way. I've got B, it goes that way. And I want to parameterize this plane. That's this whole thing.
What does that say? It says given a point X, like after R0 and like.
Given a point at X0, Y0, Z0 equal to R0 and two vectors that both start at R0. Man, that is some shitty handwriting now that I'm looking at it through the camera. How do you guys deal with that?
And R0.
We didn't do.
Is there any way you could zoom in a little? It's kind of hard to like see. Like you could focus a little more.
I don't know.
That's fine.
I would have liked to focus more, but yeah, couldn't tell you. Let's try this. This is zoomed, but not focused. Okay, how about this? And then that didn't do, that was bad. That was really bad.
I think you can.
Is that better?
Yeah, it's a little bit better.
Okay. Maybe? I have no idea. So how do I find the plane spanned by these two vectors? How am I going to parameterize this plane? Right? So let's say I was an ant and I started right here. How would I get to another point on this plane?
You follow A or B?
I follow some number of A's and some number of B's, right? Let's say I want to get to this point on this plane, right? I travel this number of B's and then this number of A's, right? So describing that process, we can parameterize this plane. I'm really going to try to write better here. Parameterize this plane by R of UV is R0, right? I'm starting at some spot. And then as Nick said, you travel A or B plus U copies of A and V copies of B. So does this make sense? This is exactly what we just talked about. We start here when U and V are 0. This is where we start. When U is 1 and V is 1, we travel 1A and 1B right here. When they're negative, we go back this way. Right?
Yeah.
Does that make sense?
Right. Yep.
Yeah. Not super sophisticated, but we have talked about it before. Okay. Who just joined?
Me.
Oh, Maggie? Okay.
Yeah.
So what were we talking about? Parameterizing planes. So what have we done? We've done graphs, surfaces that are defined by graphs, and planes. We can do surfaces that are not defined by graphs also, which is very nice. Something like spheres. So how do I parameterize x squared plus y squared plus z squared equals a squared. This is a sphere of radius a squared. Oh, sorry, a sphere of radius a.
We
Right.
put r squared in there.
Sure, we could put r squared in there. I'll put rho squared in here because that's appropriate for spheres. And we'll see what happens here in a moment. So what do we recall about spheres from chapter 15?
Like x is like r sine theta and y is r cosine theta, and then you x squared plus y squared is equal to r.
Well, those are for polar coordinates. The polar coordinates are two-dimensional, right?
Spherical
We
coordinates?
want spherical coordinates. Right, so we had spherical coordinates. They were a thing. And which is really nice because the spherical coordinates are actually a parameterization of the sphere. Right? Yes. So what were the spherical coordinates? It said x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. These are exactly spherical coordinates. I make a transformation into spherical coordinates, right? But this transformation describes a parameterization. This is spherical coordinates. And so what does that say? That says, well, my parameterization in terms of theta and phi is rho sine phi cosine theta I plus rho sine phi sine theta j plus rho cosine phi k. So all of those transformations we had before are nice parameterizations of our stuff already. Okay? So don't forget any of that stuff. This shouldn't be extremely new. Are there any questions? No? Okay. So
All that's doing is making it easier, right? Just by parameterizing it into spherical coordinates.
well, the parameterization gives us a way to walk along the surface. Just like the parameterization of a curve let us move along the curve, right? The spherical coordinate transformation made the parameterization easy. That's all it did. But there are other parameterizations I could have made for the same surface. Just like there are multiple parameterizations for the same curve.
I guess you're right. Yeah, no, that makes sense.
Okay. Okay, so 4. We're going to talk about a very important object that we've talked about before, tangent planes. So we recall tangent planes. We recall that if I have a surface, it looks like this, right? And there is a tangent plane to the surface. It looks like this at each point, right? And so this tangent plane moves as we get to each point. And we would like to parameterize the tangent plane. So how do you think we're going to want to do that? Given a surface, R of uv is f of uvi plus g of uvj plus h of uvk. What are you going to want to do? we already know how to parameterize planes if we have two vectors, right? And a point. So we need to find the appropriate vectors that describe my tangent plane. And what are those appropriate vectors going to be, do you think? Let's try to draw a picture. Huh?
Equation for the tangent plane?
Yeah, we want to find an equation for the tangent plane.
There already is. I mean, there's already like a base equation for.
There is this base equation for the tangent plane, but it's not a parametric equation.
Can we turn it into one? Or
Yes, that's kind of what we're doing, but not in the same way you're thinking. So what you're thinking about is we have an equation for but that equation really only works for surfaces. No, not surfaces, graphs, right?
yeah, no, you're right. I remember that.
So we have a surface that could not be a graph now. For example,
Yeah.
a sphere.
Yeah.
But let's draw a picture here. So I've got this, I'm gonna attempt to draw a picture. Yeah, so I've got a surface. It looks like this. It's kind of curved a little bit. And I'm at this point R naught. And I want to look at the tangent plane at R naught, right? This is this. It's touching right there. And what vectors describe my tangent plane? Well, I can see, just like we did before in our normal tangent plane stuff, that the derivative vectors, the partial derivatives, are really important to us here, right? And what does that mean? Well, let's look at this from the top down. Imagine I'm on top of this surface. I'm looking straight down, so I project it into two space. So it looks kind of like this. Imagine this is a flat down copy of that. Okay? And I'm here at, it should be in two space. R naught. This is X and this is Y. Or sorry, U and V. I wrote U and V. So there are two vectors that are of interest to me here. The partial derivative with respect to X and the partial derivative with respect to, sorry, U and the partial derivative with respect to V. This is d du. Up there is d dv. So just like we did before, the partial derivative vectors spanned our tangent plane. Right? Does that make sense?
EDU is partial with respect to X. And
yeah, but there's no X. These are U's. This is U and V. Yeah.
But that's what it would be.
Yeah.
Okay. And then DDV would be, okay, yeah, that makes sense.
Right. The partial derivative vectors span our tangent plane. Right? So if we have these vectors and a point, the tangent plane parameterized by, I'm going to call it T, UV. This is my point, R naught, plus U dr du plus V dr dv. Okay. Does that make sense? And
Yeah.
so now, how do we find the tangent plane? So let's look at an example. Find the tangent plane for the surface with parametric equations. X equals u squared, y equals v squared, and z is equal to 2 plus u plus v at 1, 1, 1. Okay. So what's the first thing I want to do? I got to find these things, right? These partial derivatives. So how do I find the partial derivatives? This is derivative of r with respect to u. So what is the derivative of r with respect to u?
Isn't it just a constant?
Why is it a
Right.
constant?
Because we
So-
don't have any u's.
Where?
Right? Like you said, like the derivative of r with respect to u. So it's not the same thing.
Well, the derivative, well, r is this, right? Let's put this into what r means, right? R is u squared I plus v squared j plus 2 plus u plus v k, right? So what is the derivative of r? If we think back to when we talked about derivatives of parametric curves, right? We take each derivative component-wise. So r of u should be the derivative of this with respect to u,
2u.
which is 2ui, plus the derivative of this with respect to u,
So 0.
0j, plus the derivative of this with respect to u, which is 1k.
Or 1k.
Okay. It should be a vector. And uv is 0i plus 2vj plus 1k. Right? So now we have two vectors. We can parameterize the tangent plane like so. 1, 1, 1 plus, excuse me, u ru plus v rv. Or we can go and, if you think back to forever ago, back in chapter 12, we can find the equation for our tangent plane, right? By finding the normal vector, right? And how do we find the normal vector?
Isn't the normal vector just like it was like the beginning values of each of our functions? Like that was a really bad description, but
Isn't that was actually my question?
Yep.
Like, does this have to do anything with like the normal and binomial vector, where we just take like the normal vector is the tangent vector, we do like the derivative of tangent vector divided by the grade or the magnitude of the tangent vector?
So the unit tangent vector is a tangent vector scaled by the length, correct? But to find a normal vector, we took the tangent vector and the displacement vector and then took the cross product, right? What does a normal vector mean? It's a vector that's perpendicular to both of these vectors. So the cross product is going to be our answer. Okay? So when we did this in the tangent spaces, in the planes description in chapter 1 or 12, sorry, God, shitty fucking day. Chapter 12, we took, all we needed was a point and one vector that was normal to the tangent plane, to the plane, right? So if we have two vectors that span a plane, their cross product will be normal to that plane. Correct? So that's what we're going to call a normal vector. Question, Nasser? You raised your hand.
That was my question.
Oh, okay.
I'm gonna put it down.
Okay. So the reason I'm talking about that is because we want to talk about the cross product and surface area. So recall, what is, so AB is a vector, normal to both A and B. What is the length of AB?
The magnitude of the cross product.
Correct, but it's a number that means something special in terms of A and B.
As in that it's scalar and that.
That is a scalar. It's the area. Remember, the cross product is the area of the parallelogram spanned by A and B. Is the area of the parallelogram spanned by A and B. So what does that mean? If I've got A, it looks like this, and B looks like this area is A cross B. The length of A cross B, okay? So why do we care? Seems like I can get through this much faster than I expected. Why do we care? Because now, just like we did before, for curves, we want to talk about surfaces. For curves, we talked about line integrals, right? So surfaces, we're going to want to talk about surface integrals, right? So we need to have a good way to describe area of a surface.
So once we parameterize A and B, that's how we can get like a surface that isn't necessarily flat, like not a plane, but like one that.
Yeah, once we have a different parameterization, a
Yeah.
non-flat parameterization, right?
And by doing so, we find by taking the cross product, we find a normal vector to both those, and it helps then cross product helps us find the normal vector, and then taking the magnitude of the cross product gives us the surface area after we parameterize.
It gives us the surface area of the parallelogram spanned by these two things. And I'll explain why we care about that in a moment,
Okay.
Or what it does, okay? So let's first talk about the goal of surface area. So I have a shape. I'm going to try to draw my picture again. A blob shape. Pretend it's smooth here. Okay. Before I forget, before I move on here, one thing I want to state or make an observation of is, when is the cross product 0? So think back to the cross product. What is the cross product of two vectors 0?
When they're perpendicular.
Same
Opposite, when they're parallel,
Parallel. Yeah, I'm sorry.
right? Because the cross product is like your hand, right? One goes this way, one goes that way. Cross product is your thumb. If they're both pointing the same way, I don't know which way to point this thumb, right? So if they're both parallel, that means the cross product is 0. If RU cross RV is the 0 vector, we're going to call this not smooth. So we're just going to say, we're going to look for surfaces whose tangent vectors never cross to be 0. And when this happens, we'll just write it here. given a parameterization R of uv, if R of u cross R of v is not equal to 0 ever, then R of uv is a smooth parameterization. And so this is how we describe what we would say is smooth, no pokey points. If there is a pokey point in my surface, at that point, the cross product of the tangent vectors will be 0. Does that make sense? So I wanted to talk about smooth surfaces before I forgot. So now we can move to surface area. So I want to estimate the surface area of this weird surface. How do you think I'm going to do it?
You should maybe pick a point on your surface.
Okay, I pick a point, and then what do I do with that point? Let's start with something simpler. Let's chop it up into a bunch of small pieces. Right? What kind of pieces should I chop it up into?
Little squares maybe, or like
Little squares maybe, but this thing is pretty curvy, so I can't promise it's going to be a square, but at least little parallelograms, right? Because they could be looking like this. They don't need to be squares, but if they're like that, that's also fine. So we'll chop this up into little tiny parallelogram-esque things, well, parallelogram things, right? You chop this up into little parallelograms. And if I want to compute the area of the whole surface, I should compute the area of each of those parallelograms and add them up, right? So how do I compute the area of this little parallelogram? Well, that's kind of tricky because it's curved, right? Imagine my parallelogram is like a little curvy like this. But if I make the parallelogram small, they should be very, very, very closely approximated by their tangent plane, right? Yes? No? Maybe?
Would like I was thinking, would maybe the projections of your parallelogram onto the XY axis, like how we did with surface area in the past?
Well, we didn't use projections last time because if we do projection, we lose the bend and the curve and the shape, right? It's going to be just flat now. And then I can't compute this little bit that curved. What were you going to say, Bob?
Basically, the same thing as Nick said. I mean, I thought that the parallelogram was always a two-dimensional space, so it's always flat. And it's kind of like that sheet of postage stamps that you put over a surface.
That's what I was thinking.
Yeah. So you have a sheet of Post-it stamps of stamps that goes over this surface at surface tangent plane, right? Let's chop this up into a bunch of little. If I had like a bunch of Post-it stamps that go over this, I can see little squares that are on here, right? There are parallelograms that are on here, but they're curved a little bit because they wrap around the hat, right? I have my Post-its, they go like this, they wrap around my hat, right? And at each Post-it, I have a tangent plane at that point, right? If the Post-its are small, the tangent plane and the Post-its have essentially the same area. Correct? And so then I can approximate the area of those post-its by the area of the tangent plane, right?
I think that's what Nick and I were getting at.
Okay, but we're not projecting. We're not going down into the x-axis. We're not being flat. We're approximating this curved object with a flat object, but it's not flat in the xy plane, like projection.
Flat in relation to your surface.
It's flat.
Like, as in that how it kind of, it's so small that it essentially is flat
Yeah,
on the surface.
on your surface, yes. Right? It's like how the Earth looks flat when we're here.
Like when you said you're an ant, and these are little.
Yeah. Or even now, the Earth is large enough that where I'm standing, the Earth is flat. Right? That's exactly what we're doing. We're just zooming in on small bits where it looks real flat, and then approximating the area with the tangent plane. What is the area of the tangent plane?
Magnitude of the cross products.
The magnitude of the cross product. We just talked about it, right? So if we have given a surface S parameterized by R of UV, the area of S, the surface area, is just the area of this integral over the area of each of the tangent planes. We skipped a little sum step up here, but does that make sense? This right here is the area of the tangent plane. Imagine I'm adding up a bunch of small ones, and that's what this integral is.
That's the area of, wait, so the magnitude of RU cross RV, that's the area of our entire surface?
No, this is the area of the parallelogram spanned by RU and RV at a specific point.
At a specific point. That's because RU and RV are the change.
Are the tangent vectors at a specific point. And so when I vary all these points around, I get everything and then add them all up. Right? Nothing super sophisticated. Just compute something here, move it a bunch of places, add it all up. Okay? So let's look at an example. What time is it? We'll look at an example. Why not? So what's the surface area of a sphere? Of the sphere of radius A. We'll do rho. So what's the parameterization we had for this? R of theta phi was rho sine phi cosine theta I plus rho sine phi sine theta j plus rho cosine phi k. This is the parameterization we had for the sphere of radius rho. And so now we're just going to compute the surface area, right? What is RU? I guess in case R theta is the derivative of this with respect to theta, which is minus rho sine phi sine theta I plus rho sine phi cosine theta j plus 0 k. Just taking the derivative with respect to theta. R phi is rho cosine phi cosine theta I plus rho cosine phi cosine theta j minus rho sine phi k. Please check my arithmetic. Ugh.
Isn't the K term of your R sub theta vector 0? Because there's no,
Yeah, it's 0. This is 0 times k.
yeah, oh, it's a 0. Okay, it looked like a delta or something, sorry. Maybe a 5.
0 times k. Right?
What's that symbol called? It's like the theta, but not theta.
Oh, phi?
Yeah, phi. For the R of phi, isn't the rho cosine phi, shouldn't it be like rho cosine sine theta? Or like rho cosine phi sine theta in like the middle part?
Oh, yeah, right here?
Yeah.
Yeah, I just wrote the wrong thing, correct. That should be sine theta. Yes. Correct. Bad arithmetic there.
Isn't there an equation for surface area of a sphere?
Of course there is. But, I mean, the purpose of this is to illustrate this technique for surfaces that don't have equations for them.
But wouldn't you only use this parameterization of just like of spherical coordinates?
Yes, I wouldn't use this parameterization to describe a different surface. But the idea is, if I had a parameterization, I can use this technique independent of what the parameterization is, right? This is just one example of how this technique works, but in theory, I should just be able to do this with any parameterization. So, yeah, if we wanted to compute the area of a sphere, I would just look at the equation, and I think it's like 4/3 pi r cubed or whatever. Could be wrong. I really don't remember. Maybe 4 pi r cubed. I don't know. Maybe 4 pi r squared. I would Wikipedia it and it'd tell me. But we're not interested solely in that, right? So now I want to take the cross product of u and v of these two things. R theta cross r phi. And the magnitude. This is, oops, just drew on my screen there. This is I, J, K, and I'm gonna lay minus rho sine theta cosine, sorry, sine phi cosine theta, rho sine phi cosine theta 0, and rho cosine phi cosine theta, rho cosine phi sine theta minus rho sine phi. So I gotta take the cross product, which means I gotta find this vector and then take its length. Okay. It's a lot, seems like a lot of effort. Does it cancel out real easy? Hopefully. Yeah. Let's do cross product. If you did the cross product, you would get this thing, a squared sine phi. You get lots of cosine squareds plus sine squares, and those are equal to 1, and then you factor. This is some trig follow up. Not super hard. We could go do it. But we're going to go there.
The cross product of those two is a squared sine.
The length of the cross
The
product
mag-
is,
that's right,
yes.
the one.
Right, the cross product is a vector. So the surface area is going to be the integral of, over this whole thing, dA, which is theta goes from 0 to 2 pi. Phi goes from, 0 to pi of a squared sine phi d phi d theta. All right, phi goes from 0 to pi, and theta goes from 0 to 2 pi. So I keep that. And we can integrate that if we wanted. Yeah, don't really care that much though. Okay, should be pi, 4 pi. I think we get 4 pi a squared. The a squared comes out. It's in the integral of sine from 0 to pi, which is not 0 because we only take half of it. It should be pi, and I get no. Should be 2, something like that. Yeah, we can compute that. We should get something good. Not the best example there. Probably should have picked an easier example. But it was a good parameterization, and the computation got a bit messy. Any questions? There were probably many of them. That was a shitty description. So let's recap what we did. Parameterize. We give it a parameterized surface. We find the tangent vector derivatives, RU, RV. Compute the cross product, and then take its magnitude, and then go hit this formula. Okay?
In that formula, it says cross product of r sub theta and r sub u.
This should be a phi.
Phi, okay.
Yeah, too many letters there. Okay. Any questions? So in the special case where we have a graph, a surface is the graph of a function f of x, y equals z. What was our parameterization? X is equal to u, y is equal to v, z is equal to f of x, y. Right? We had a really nice parameterization. Correct? So R of u, what is R of u here?
Just one.
R of u is a vector, right?
But we don't know what the function is.
This is our parameterization right here.
Yeah, but you're asking for like that, but with respect to u, right? The derivative
Correct.
with respect to u.
Yeah.
We don't know what the f of u v is, like z.
Yeah, sure, but that doesn't matter. We should be able to get a description for u, the derivative of r with respect to u in terms of these things, right? What is the I component of R of u?
1,
1.
1i, 0v, and f prime of u. Or something?
Yeah. df du
U of
k. Right? And then R of v is 0i plus 1j plus df duk. df dv, sorry.
Yeah.
So now we're going to compute the cross product, RU cross RV, and I'll save you a computation here and say that this is df du I minus df dvj plus k. So what is the length of this vector?
The sum of all those components squared,
Yep, which is?
something.
Okay, tell me what I should be writing here.
I guess dfu squared plus dfdv squared plus
1 squared, right? So in this case, when the graph is the graph of a function, when the surface is the graph of a function, we have a very nice description of the length of the cross product. Right? So that says if a surface is defined by f of x equals z, then the area of S is the integral over the region of 1 plus df dx squared df dy squared dA. Okay. Any questions? So we could just find, let's go look at an example here. Let's do an example. Compute the area. Of the surface given by f of xy is 3x squared plus yx over we got a little sheet. What's the surface area of this sheet?
Can we just do like square root of 1 plus, partial derivative of x plus partial derivative of y, and from 0 to 2 and like that?
Seems reasonable, right? Our region is very nice. It's just a rectangle,
Yeah.
right? So we should just be able to set up this integral from 0 to 2 and 0 to 3 of the square root of 1 plus, what should go here?
6x plus y squared.
Squared plus
2yx.
2yx squared dy dx. So in the case where I have a surface that is a function, is pretty straightforward. Okay, any questions? No? Okay. Who's here? Okay, so we got, okay. So we'll take a moment to, Yost is not here, but I'll pose this, I'll take a break, and I'll pose this final exam idea to you guys now. Think about it, and then on Tuesday, we'll have a chat about a vote on it, okay? So there are two options for this. One is I write some bullshit Canvas exam, and you guys can take your final there on Canvas. And two, I write a normal exam, and we continue scanning it and things like that. But since I am not going to be here, I can't monitor you're doing anything. The exam will be open notes and open book. But consequently, it will probably be much more difficult. But you'll have your equipment, books, computers, anything other than people.
What's the Canvas option again?
I write a exam that is on Canvas, that you can take on Canvas, and Canvas tools can restrict you from doing stuff. And it's going to be probably multiple choice or fill in the blanks. You will get no credit, no partial credit, because Canvas won't score partial credit. It can't give you your work.
Okay.
So those are two options. You missed the beginning of why we can't do this anymore, but the administrative.
Yeah, sorry, I'm having trouble with the schedule, and I completely forgot about the class.
Yes, the administrative council said I am no longer, not just me, the entire
No, I
college
know.
is no
I
longer
know,
allowed
yes.
to proctor exams over Zoom for legal reasons.
Yep.
So,
Would you time us for the final? Like, would it be a...
yes, it will be timed. So that means when I allow you to view the final, you will have some number of minutes to ensure that it is in my inbox.
Will the final be like previous tests where if we just, do homework and stuff, we should be...
Well,
Yeah.
that's going to be the difficulty. If it's open notes and open books, and obviously not, because you can just look at the homework assignment you already did.
Yeah.
The concepts will be the
I don't like
same.
the open note idea. That's probably not the way to go.
The concepts will be the same, but the problems will have to be different.
Mhm.
Well, may I suggest something? In our differential equations class in Canvas, there is a button that says file upload. So like in our tests, this man just puts like the questions, and instead of an answer choice, it just says upload file, and then he times it. That's how we do it. So we get, it's a lockdown browser, so you can't go surf the internet, and it's timed, but then you upload the file at the end.
So you're saying, but do they keep them separate?
What do you mean?
When individual students upload files, do other students see them or no?
No. It's a Canvas test. So you open it, and like the timer starts going, and instead of answer choices, it just says upload your file.
Oh, it's a Canvas test. I see.
Personally, I like the open note, open book one.
You're not when you take it, man.
Yeah, no, I would love it better if you just time us and make sure we cannot go and look to any other, I don't know, source or resource or whatever.
Like
I
in
mean,
Canvas, there should be a like that's how we do it in differential. There's a button that instead of an answer choice, it says upload your file. We upload the
Yeah,
file, and then it
but so that's fine and dandy. You can't use your computer, but I mean, what stops you from using a book?
Yeah,
it's timed. Like you don't have time to go riffling through your pages.
I mean, you do. If you just go through the chapter.
I mean, you could just open the book to the chapter, read the equation, and copy it down, right? So, and I still haven't found this Canvas test thing, but I will look into that. They have this. I'm sure there's an option here for Canvas test. I can go look it up. I'll have to think because you could just look at your book. It's right there. There's nothing that stops you from doing it. So those are the options. Now we have 3 options. A normal Canvas test, this open book, open note test that will be timed, and Canvas problems that are timed and you submit files. We'll have to see, I guess. Let me think about it a little more. I'm going to go explore this Canvas test option, and then we will group on Tuesday and make a decision.
But can you also do the fourth one? Like you brought up at the beginning, like if we sign a waiver saying that we're not
No, we
disabled-
can't do the waiver thing. I already asked the dean about waivers.
What's
Okay.
that?
Yeah, I already asked her about waivers, and she said no. So the waiver thing is a no-go. Yeah. Which is unfortunate, because I thought that would be the easiest solution. Okay, so where do you go to Canvas test here?
I mean, well, let me just pull up my differential equations class real quick. Dashboard, differential. So there's a tab that he has here that's quizzes. And then when you open it,
Oh, I see. I just got to start a quiz.
yeah, and you should
Okay.
be able to time it.
Yeah, that's fine. Okay, but then we'll have to decide how we're going to want to do that. So think, and we will come up with some decisions on Tuesday on how the final is going to be done. There won't be any more quizzes for the rest of the semester since there's only a week left and then the final.
Mm.
So, yeah. So just be one final. We will have a decision on how we're going to do the final on Tuesday. Okay. Anyone who is not here on Tuesday relinquishes their option to vote.
Okay, and for the final, what percentage is going to be from the last chapters, and what percentage is going to be from the whole course?
They should be pretty uniformly distributed amongst everything that has been on an exam so far. So the most recent stuff will be slightly more heavily weighted than the other stuff
Okay,
because there wasn't an exam for the most recent stuff.
yeah, makes sense.
As far as what distribution, I couldn't tell you, but we think about it like 25% of the stuff will be on this most recent stuff since the last exam, and then 75% of the stuff will be everything else.
Okay,
That should make every topic almost even.
all right.
Okay. Any questions on how we're going to do that? Show up on time on Tuesday, please, so we can have this discussion at the beginning. Okay? So back to math. So we just spent this whole 40 minutes talking about surfaces and surface area. What do you think we're going to talk about next?
Volume.
Not quite. So let's go back to the curve stuff. We talked about arc length, and then we talked about what?
We talked about curl and divergence and stuff.
But that was much after we talked about line integrals, right? We talked about arc length, and then we integrated functions over the curve.
Force? Like,
Arc length and line integrals, right? We integrated stuff over the curve. So now we're going to do integrals of functions over surfaces, right? So what I mean by this is, let's think about, so this is 16, 6, 7, this is surface integrals. So before we did integrals like this, we looked at this region D that was flat in the domain, in the XY plane here, and we integrated this height. And the integral was this area, right? Now, I want my region to be this weirdly shaped surface here. And my function is on this weirdly shaped surface, right? Maybe I could think of this as like a heating pad, and the function is a temperature at any given point, right? Or it's some weird region, and the function is the density at that given point, or the mass, right?
so the function that you're looking at, it goes through your surface or is on your surface.
It's on my surface, yes.
Okay.
Okay. So what does that mean? I've got some, try to draw a better picture than this. Pick a nice thing that I can draw a picture of. There, okay. I got a little slide thing. This is my surface. I chop it up into a bunch of little boxes, right? That's what we do. We chop things up into boxes. Okay, and I want to compute the value of the function over this small region right here. Right? Does that make sense? How do you think we're going to do that?
We used like parallelograms earlier.
Yep.
Kind of
But in the simplest sense, all we need to do is multiply the value of the function here by the area of this box, right? That's what you talk about parallelograms. The value of the function times the area of this box. So the value of the function, that's f of some point in here. This is Pij star. And the area of the box is, I'll call it delta Sij. And delta Si goes to 0, right? I want the boxes to get nice and small, right? So I can define the surface integral of f of x of f, I don't need f of x, y, but surface integral of f over s, the surface, as the integral over the surface f of x, y, z, ds is, we need to limit the limit as n and m go to infinity. The value of my function times the area of my box.
The value of your function, though, that spans an area. Like, it's not a specific point. It's
True. The value of my function could change within this box, right?
yeah.
But let's say I make my boxes really, really small. So what does that mean for the area, the value of my function over that really small box? It should be essentially the same,
Pretty much the same, yeah.
right? So that's what we're going to do when we take this limit. Things are going to get really small. Okay? So how do I compute this thing? This thing is a tricky thing to compute, right? This is going to be the area of that parallelogram. And how do we compute the area of that parallelogram?
Cross product or magnitude of the cross
The
product?
magnitude of the cross product, right? So what does that mean? We need to make a parameterization first. So using stuff from before, we parameterize the surface. So let's parameterize S. So let's say R of UV is a parameterization. Of S. So then delta Sij is essentially equal to Vj. R, there's no J here at all. Ru cross Rv du dv. Right, this is the area of that parallelogram we were talking about. Right? So then we should be able to just replace this in our integral into this sum and take the limit. So we can say that the integral over the surface of x, y, z ds is equal to the integral over the region d of f at r of uv times ru rv dA.
Is dA delta U delta V?
Yeah, it's just the area, depending on how I want to choose to chop up my region D.
Okay.
Right? I can chop up my region differently. So if I want to do polar coordinates or whatever, I would have a different dA, obviously.
It just depends on your parameterization.
Depends on my parameterization and how I choose to chop up my region when I integrate. Okay? Does that make sense? So let's make a quick observation here. Okay. We have a function, technically of 3 variables here. And we can compute this integral by parameterizing and computing a surface area. Okay, so let's do an example. Let's go find a nice example. Okay. So this is 9. Let's pick a nice example. And let's do compute the integral over S of x, y, z ds, where S is the cone with parametric equations. X is equal to u cosine v, y is equal to u sine v, z is equal to u, 0 less than or equal to u less than or equal to 1, 0 less than or equal to v less than or equal to 2 pi. Pi over 2. Good. So we're just going to go and follow the formula, right? We have a parameterization. So what do we do?
Find R of u and R of v.
Okay. What is R of u and what is R of v?
Like the partial of R with respect to u.
I mean, what is it?
Oh, it's the u cosine v in the x.
Yeah, this is a u cosine v.
Be cosine v then for the I.
Just go ahead and tell me what to write for R of u, the rest of R of u.
Plus sine of vj plus 1k.
Okay. What is R of v? Someone else? Somebody else? Start at the top. Darius is at the top. I think it's alphabetical. So no, it's not. Anyways, Darius, what's R of v? You're muted if you're saying anything.
I'm sorry, like your screen, I can't really see your writing. Like it's either my computer or your glare. I'm trying to see. So x equals cosine of
Anybody else having glare problems?
Yeah, but it's not too bad.
Okay, well, we'll fix the glare problems. We'll just move on. We'll just do this fast. U sine v I plus u cosine vj plus 0k. Right? Now we compute RU cross RV. This is cosine v sine v1 minus u sine v u cosine v0 I j k. Okay. This is minus u cosine v I plus minus plus u cosine, no, u sine vj minus plus. Triple minuses. Okay,
That's
let me get
minus.
this. It's a minus sign. Triple minus. Yes. Minus from this one, minus from this one, and then that one. Plus cosine u cosine v squared plus u sine squared v So it's minus u cosine v I minus u sine vj plus u squared k. What's the length of this vector? Is this thing squared plus this thing squared plus this thing squared square rooted. So it's square root of u squared plus u to the fourth.
I'm sorry, can you back up there real quick? So you got u squared. So where did you get the u to the fourth again?
I squared this thing. Oh no, this should be a u. Sorry, this should be a.
That was, yeah.
This should be a normal u, not a u squared. So this should be a u squared.
Yeah, okay, that makes a little more sense.
So then I get square u times the square root of 2. Right. And so now my equation says I evaluate my function on my parameterization. Right? So I get the integral of from 0 to 1 of 0 to pi over 2. Those are my bounds given up here. And I evaluate this thing at my parameterization. So that says u cosine v, this is x, times u sine v, that's y, times z, which is u, dv du. Okay? And then I compute. Any questions? This is essentially just follow the formula.
Could you explain how the magnitude of RU cross RV relates back to that integral at the bottom?
Oh, because it doesn't, because I forgot to put it in there.
Cool.
Yeah. Follow the formula, but actually do it right. Yeah. Okay, now that I put this in there, does this make sense now? Okay. So we can just compute this, nothing super difficult. We want to talk about one last thing before we go. Like I said, we're not going to finish the rest of this section today. We have to talk about flux next, but to talk about flux, we got to talk about orientation. And so what is that? What do I mean by orientation? We live in this really nice world where most things have two sides, right? There's an inside and an outside. Our homes have insides and outsides, other things like that, right? So when we talk about a surface has two sides. A surface has what we would call up or down, right? Imagine I have this piece of paper and it goes on forever, right? This is what could be considered the top side, and this could be considered the bottom side. Or if I have a sphere, right? There's the inside of my sphere and the outside of my sphere. Okay? So we call those kinds of surfaces orientable surfaces or oriented surfaces. Surfaces that have some notion of inside and outside. Okay? And we're going to need to know about how do we define inside and outside? By the normal vectors. Right?
I have a question.
Yep.
Wouldn't inside and wouldn't inside and outside only relate to like closed surfaces? Like,
So yes, if they're closed, right? But we don't necessarily need to. I said another way we can describe them is top and bottom.
okay,
Right.
yeah,
So if I had like an infinite plane, it would have a top part and a bottom part, right?
so that's what you. All right, yeah.
Yeah, I mean, you can use the metaphor inside and outside or top and bottom depending on what kind of object you're talking about. But if I have, is true. If it's not closed, I won't have it inside. Okay, but I'll have a top and a bottom, or a left and a right, or whatever. As long as can I distinguish direction on my surface? That's all I really want to say, right? An orientable surface is a surface in which I can make a distinction between direction.
So a Möbius strip would be an example of a surface that is not like that.
Yes, because I can't make a distinction on, or another way to say this, which is easier to describe in the Möbius strip, does my surface have two sides? Right? An inside or outside, an up or down, a left or right. Does my surface have two sides? If it has one side, it is not orientable. If it has two sides, it is. Okay? And we can, how do we do that? We can think of, if I'm on this surface, imagine this is my surface, I'm at this point, I have two choices of normal vector, right? The one that comes up and the one that comes down. And as I move along the surface, I always have two choices of normal vectors, right? The normal vector that was on top never becomes a normal vector that was on bottom. The one that's on top specifically stays on top. So the normal vector, when we look at the Möbius strip, that is a surface that has one side, because when I start with one normal vector, I can actually get on the other side, there's only one side, but the other side of the Möbius strip and trace the entire strip and get back where I started without changing directions, right? Because imagine I had a sphere, right? Imagine a sphere. And I have a normal vector pointing out of the sphere, right? And I move my sphere around, my normal vector around everywhere, around the whole area of the sphere. I would cover everything on the outside of the sphere, but not the stuff on the inside. If I want to cover the stuff on the inside, I have to put my normal vector inside and then move it around. But if I had the Möbius strip, I could cover everything on the Möbius strip without changing the direction of my normal vector. So that's an example of a non-orientable surface. And we're going to talk about orientable surfaces. And we'll go into more detail about this on Tuesday because we're a little late on time. But we're going to be talking about flux through orientable surfaces. And we need to know which way is up and which way is down to determine which way is through. Okay, questions?
What about surfaces with holes in them?
Surfaces with holes should still be orientable. Like the torus is orientable. Imagine I have a donut with this hollow inside. There's the inside of the donut and there's the outside of the donut.
Yeah, I guess, yeah, it's still matter, yeah.
Yeah, imagine like an inner tube.
Yeah.
Right? Or a tire, right? The air on the inside is completely separate from the air on the outside. That's why tires work. There's clearly a hole in the tire in the center where I can attach it to my thing, my car, right? So yeah, we'll stop there for now. We'll finish orientable surfaces and surface integrals and flux tomorrow, Tuesday. And we will chat about what's going to happen during this final. Okay, so please show up on time, if not early on Tuesday. If you do not show up by 12:35, your voting rights are gone because we're voting before then.
I bring up one more thing.
Yes, Darius.
So, like my other math teacher, the differential equations, he's kind of in the same boat. And something he floated was that he was just going to take the final and like take the weight down and like increase the weight of the exams that we were actually present for. So like, I don't know if you were interested in doing that or not.
I haven't thought about changing the grading scheme, but I don't.
He thought
I
that
don't
made
actually,
sense.
I don't remember what it is now, but I will think about those things when I think about them, which will be before Tuesday. Yeah, that's a reasonable idea. Any other last minute questions? I can't hear you, Maggie, if you're saying anything.
No, I'm not.
Okay.
This is Bob.
Yep.
If you just want to see some fun stuff, Google images for non-orientable surfaces.
Yeah. Well, the only one you can actually really see is the Mobius strip and the Klein bottle. But the Klein bottle is technically a four-dimensional surface,
Yeah.
so it's not really drawable in 3 space. But
Right.
one of my friends in grad school was a topologist, and he had an actual Klein bottle that was made of glass in 3 space. It was pretty cool.
Yep.
He put some water in there, and he never got it out. So it's a surface with one side, even though it's a 3-dimensional object. Okay, so have a nice day. Have a nice weekend. See you Tuesday.
Thank you.
Me too. Thank you.